Swayam Prabha. Digital India. Educated India.
So what we so far discussing is just like we know in some applications we will be interested in knowing a priori whether this state is going to be positive recurrent, null recurrent, or it is going to be transient, right? Like in the insurance kind of applications we just discussed last time, we said that it is important to know whether this is a recurrent state. Like if I am going to go bankrupt, the state that I am going to become bankrupt is going to be recurrent, I do not want to be in that business, right. So a priori, if you know or if you could model all the system, you want to quickly identify whether this state is going to be positive recurrent, null recurrent, or whatever it is. So we are just now stating what are these results that you can what you can say about that just by looking your Markov chain, right. See, like all this characterization was only simply based on your FJJ values, right. FJJ values which you can compute from basically your transition probability matrix. So your transition probability matrix is basically characterizing your Markov chain. So if I tell you my Markov chain, that you can quickly come up with your transition probability matrix. From that you can compute this FJJs and try to identify, okay, what are these states, how they behave like. Now based on this you can try to understand how your things are. Like for example, your transition probabilities, you may start with one transition probability matrix, and for that you observe that, okay, these three states are transient and these are recurrent and all, but you notice that I am going to be in recurrent state most of the time, so this is a bad case, I do not want to get into this. So let us change my Markov chain. Changing Markov chain is equivalent to saying that, okay, let us consider these parameters. You want to look at a different set of parameters, that is like you changing your design, or like you changing, okay, let us instead of starting with this much capital, maybe let us start with another set of capital or something like that. And then you analyze based on that, okay, what are the states which are going to be positive, recurrent and transient. Then you will see that, okay, in this I find that my recurrent states are less, maybe this looks like a bit safer bet, and then I want to maybe go with this. So what we are just trying to do is, given this set of inputs, given one description of Markov chain. See, Markov chain, as long as somebody tells you, okay, these are the transitions happening, you have a Markov chain, you are identifying. But that Markov chain, it can change if you change the parameters, right, your transition probabilities. Once you have a new set, you can do the same thing. So you can do this analysis for any given transition probability matrix, and based on that you can say, maybe like you say that, okay, this transition probability looks like it will lead to a situation where things are less risky, and maybe as a designer or the guy who is actually going to implement them, maybe he will see how he can get those parameters. Okay, fine. But for this computation of all this null, transient and null recurrent, we are really do not need to worry about my initial probability. I only need to worry about transition probability matrix, because as you seen, when I was trying to do all this calculation, I stayed given this state, I kind of fix my state, and from there I am trying to analyze. So the initial distribution is not affecting much, right, because you are already fixing a starting state, and after that you are analyzing. Initial distribution only affects in which state you are going to start from, but that you are already fixed. Now what is only going to decide how your future is going to evolve is your transition probability matrix. So that is why I am saying, to analyze this, all you need to know is only transition probability matrix. Okay. Now We know that we have these different states. As of now, you have classified them into two broad categories, transient recurrent and further positive recurrent and null recurrent. Now, is it possible that all my possible states I can group into these classes, or like let us say I can group into some classes, and what is the property of each of these class. So, let us try to understand that through what we call as communicating classes. Okay, let us define something. So, let us take a Markov chain where the state space is some countable set, okay, as we always denote it by S, as I am again denoting it by S, which is countable. Now, we are going to say that so let us take a DTMC with countable set of states. Now, take any state j and take another state I. I am going to say that j is reachable from I. That means I am going to hit state j starting from state I if there exists n positive such that this n step transition is, the probability of n step transition is going to be strictly positive, and in that case I am going to denote that I goes to j, that is from I can reach state j. See, as long as all I need is to reach j from I is at some point, at some time I should be able to reach it with some positive probability. Okay. Right now this n could be very large, but that is fine, as long as I can do it in some time, that is fine. Now, we are going to say that you take two states I and j, if I can reach j from I and vice versa, like also if I start from j at some point I go back to state I, if that happens then I am going to say that state I and j communicate. Okay. So, if I is reachable from j and j is reachable from I, then I am going to call I and j communicate. Okay. And that communication symbol I am going to use it as this double arrowed line. Okay. When I say j is reachable from I am going to use single arrow taking I to j, and when I and j are communicate, I will use this one. Okay. Now this is a relation, right? What is this relation? This is a communicate relation. Now we can show that this relation is equivalence relation. So how many of you know equivalence relation? What are the properties? Reflexive, symmetric, transitive property. What is reflexive property? Self? Okay, so reflexive property. Does this relation satisfy reflexive property? So then for that what I need to check? I going to itself, right? So if this is the case, what I need to show? I is reachable from I, and again I is reachable from I. To show that, what I need to show, there exists some n positive, n greater than or equals to 0, so that I can go from I to I with positive probability. What is that n? 1 or 0? 0, right? Because Pii equals to 1 by our definition. If you are in I, you go to there in 0 time with probability. That is the meaning of Pii 0. That is what we have defined like, right? So that means with probability 1, if you are in the state, in 0 state, you will be there in 0th round. So this trivially holds. Now second is symmetric. What does this mean? J, then this implies, right? Is this true? So what is, I mean this is, so what is I? Let us take I communicates with J means, right, I is reachable from J and J is reachable from I. So that means there exists some positive probability, some positive finite time in which I should be able to reach one from the other, right? That is same as, so here you start from I and go to J, and then when you look at the other direction, you start from J to I, and just do, I mean, the same thing here. Yeah, yeah. This is also other direction. If you just, okay, this is also. But in this case, we just need to argue that this implies this. If you start with this, then you can say that this implies this. Now what is the next? So what is, how to show that? Is this true? So how you are going to show this? So let us show one direction, like I communicates with K. So I communicates with J means in some finite steps I go from I to J, and again J communicates with K means in another finite step with positive probability I go from J and K. So if you take this product, I know that in this many rounds at least with positive probability I go from I to K, and similarly the opposite direction. So this relation is an equivalence relation. So what is the property of an equivalence relation? This relation partitions, but the thing is it partitions your class. So you have this state space S this relation if you apply, it is going to partition your S into what we are going to call as equivalence classes. So that means all the states within, when you have partitions, and if you take one particular partition, in a way all the states in that partitions are going to be equivalent. That is what we call as equivalent class, and here all this we have so many classes, so we are going to call them as equivalent classes. Okay, fine. We have some more definitions. Once you have a equivalence relation, this is clear that it partitions. Now equivalence class is just like the classes we have in this partition, we are going to just call them equivalence classes. Okay. So proof for this, work out yourself. Just ensure that you will not get any overlapping sets. Okay. Okay, now let xn is PTMC on S. Okay. So let us say I have a DTMC with transition probability matrix P. Okay, then so we are going to, as we said, S is going to be partitioned by this equivalence class, and the different classes we are going to get, we are going to call it as communicating classes. Okay, because we know that each pair in that particular class or a particular partition is going to communicate with each other, right. So we call them as communicating classes. Now you take a communicating class, So, if you are going to take one communicating class and you are going to take one element in that communicating class and take state which is outside this communicating class, okay, and if let us say I belongs to that communicating class C and J is outside this communicating class, if Pij is equals to 0, then we are going to call this communicating class C as closed. That means the probability of you going from any state of this to outside state of this class is going to be 0. That means you are not going basically outside of this class to any state. So, you are, that is the kind of closed class you have. And if this does not hold this property, then we are going to call it as open communicating class. Okay. Now, we further say that the transition probability P is going to be irreducible if there is only one communicating class. That means entire state space is just one communicating class, right, and in this case, so and this case we say the Markov chain itself is irreducible. Okay, again to define this communicating classes, all what I need to know, is this enough if I know my transition probability matrix? Yes, right, because to define this I need to know all these n step transition probability matrix, but we are in the case of time homogeneous Markov chains. For this Pij's n step transition probability can be obtained from my one step transition probability matrix. So, all these properties that I have defined, that this relation, whether it whether my class is going to be communicating and whether my class, this communicating class is closed or it is going to be open, all I need to know is just my transition probability matrix. From that itself I can define all these things. And now whatever the transition probability I am going to deal with, I am going to call it as irreducible if that leads to me only one communicating class, so that my state space is not going to be partitioned, it is just going to be one communicating class. So, once I say one communicating class, I should be reachable from one state to another state within that communicating class. So, that is why I am going to call it as irreducible. You can't partition into two parts if that is the case. So, in that case we are just calling our Markov chain itself is irreducible. Okay, a quick example on this. Let us say I have some states like this, where can go from here, go from here, go from here, go from here, and also go from here. So, the points where I have put these arrows, that means these transitions are possible with positive probability. Where the link does not exist, that means that transition is happening with 0 probability. So, let us call these states 1, 2, 3, 4. So, how many states are there here? 4 states. And how many communicating classes are there here? What are those communicating classes? 1 and 2, because I am able to reach 1 to 2 and also 2 to 1. And what is the other communicating class? 3 to 4, right? This also I am able to reach one from each other here. And now, is this communicating class a closed communicating class? So, this is one class, let us call this C1 and this is called C2. Is this communicating class a closed one? Why is that? Yeah, we can go with positive probability from a state in this class to a outside state C2, whereas this C2 is going to be a closed communicating, sorry, it is a closed one. Yes, right, because we are not going anywhere outside. So, what if I add another states here? and allow this to happen. So in this case, if I add this, will this 5 goes inside C too? But can I reach from 5 to 1? So I can go here with positive probability, or from there I can go here, right? In that case, I will include this 5 also in that. But suppose if I remove one link here, it's that can become another itself a class, right, with just one element in that. And in this case, 1 and 2 is going to be closed one. It's not going to be closed one, right, because it can escape from this 2 to a state which is outside this class. No, we are saying closed. This one we are going to say closed if we do not have any escape route to go outside a state with some positive probability. So in this case, when I wrote this, right, do you have any escape route to be outside, go outside to state other than 1 and 2? You go 1 and 2 and then 1 and 2, you may just be like that, right, you will not possibility. And here there is a possibility for you that you escape from being in C1, you can go to here, right, because there is positive probability. Now if I just say there is, I add 1 and then let you go there, then you are able to escape from this class. So that is why it is no more closed. Okay, now comes, it's called class property theorem. If there is only one thing, what is there? To define closeness, it is just going to be closed, right? There is only one state in that, and the definition becomes kind of vacuous here. It is just one state and you have to go into that state. Okay, so when I say it comes to this state and it is not going anywhere, means it remains in this state always. It is just staying in that, not moving anywhere. Okay, now the states in So this theorem is stating that the communicating class we have will be such that all the states in a communicating class are going to be just one type. They are all either going to be all transient, are going to be all null recurrent, or going to be all positive recurrent. It is not possible that you have a communicating class that will have some states to be recurrent and some other states to be positive recurrent or null recurrent. It is going to be either one of them. Okay. So let us quickly look into this, why this is the case. Suppose let us take one communicating class and let us C be a communicating class. And take Ij belongs to C. So if Ij belongs to C, what I know, let me write it as K. What I know, there exist R and S such that P j k of R is going to be positive and P k j of S is going to be positive, right. This is by definition. If I and j belongs to the same communicating class, it must be the case that I am going to go from j to k with positive probability in some finite steps, and similarly I should go from k to j in some finite step with positive probability. Now suppose now I want to claim that if I assume that j is transient, I want to prove that then k is also transient, and if I assume j to be positive recurrent, then I want to show that then k is also positive recurrent, and if j is null recurrent, then k is also null recurrent. So let us see why that is the case. Okay, let us first look into the case where I want to go from j to j in this much steps r plus n plus s. This r and s I am going to be take this whatever this value, n is variable for me, any n. Now what is this? This is probability that x r plus n plus j for s is equals to j given you are going to start from x naught equals to j, right. This is the meaning. Now what I will do is I will, instead of going from state j from the beginning to again state j in r plus n plus n steps, I will want to reach this while going to some states in between also. So let us further condition this by saying that r n plus s is equals to j. What is the conditioning I want to add? X r equals to k, then x r plus n is equals to k given x naught equals to j. So what I want here is, yes, instead of directly going here, I also want it to be first reach state k in the first r steps, subsequently in the next r n steps, that is r plus nth round, I want to again hit state k, and from there in the next n steps, that is r plus n plus s round, I want it to state j. So is this probability is going to be lower bound for this? Yes, right, because I added these two extra conditions on this. I am basically asking this Markov chain to go through this special state at these steps, not just looking at the final step here. So if you just now apply the chain rule here, what you will get is so I already applied the chain rule and the Markov property here, and by definition the first term is going to be P j k in R rounds, then P K K in N rounds, and then P R L going to be J J. Now this is K here. This is going to be K J in S rounds. It is correct? So I have just applied chain rule and apply Markov property, and this is just by definition. And now what we have basically done is P J J R plus N plus S is going to be less than or equals to P J K R P K K in N steps, and then P K J in S steps. Now I want to use this property. First thing, you can check that P J J of N, you are going to be P J J N plus S. This I am simply going to take N greater than or equals to 1 here, and this one here. So this is because I am just taking this guy is a lower bound, sorry, this guy I have a lower bounded and then summing it over all possible n's. And now further I am going to lower bound this by this inequality which I have obtained here. So here S is the variable, this R and S are fixed, and I know that this P J K R and P K J S both are strictly positive quantities. So now let us use the property that we have stated in a theorem. Suppose if I assume J is going to be transitive, let us assume J is transitive. Sorry, transient. So suppose if I assume J is transient, what I know about this quantity as n goes to infinity? We just know it is to be finite, right? I know that if my state J is transient, this is going to be finite, right? And I know that this quantity here is some positive quantity, and this quantity here is again some positive quantity. If that is the case, then what I can say about this quantity? This is also finite, right? Then what did we say in that theorem? If that the theorem, when the summation Pij n is finite, if and only if J is transient, right? That theorem was if and only if case. So now if I assume this quantity to be finite, let that is following making assumption that J is transient, then I am already concluding that this guy is also finite. What does this imply? What is transient? So that implies K is also transient. So what if I take any two states J and K in my class, what we are concluding is if J is transient, so is K. So it must be the case that any states in this communicating class, they must all be transient, right? Okay. So now let us look at the case where I is, sorry, let us look at the where J is now, we want to look at null recurrent. Let me see what I want to look at. Okay, now let us say null recurrent. Now we are going to say that if J is null recurrent, then we are going to show that K is also going to be null recurrent. Okay. Suppose let us say J is null recurrent, and if I assume that that implies K is transient, but then I am contradicting my first statement, right? If suppose K is transient, then it must be the case that J must be also transient, but I am assuming that J is null recurrent. So by this contrapositive argument, this can't be the case. So J could be either null recurrent or positive recurrent. So let us see what it is. So we have to then use the another result we have used, where instead of looking at the sum, we look at their averages. Okay. So let us try to look at the average. And then this I am going to write it as 1 by n so just we have few steps will be done. Okay, what I am doing here is basically I am taking this 1 by n and the summation of the n terms here, that is the average of the first n sums here, and then in this I am going to drop out all the terms before r plus s and looking at the sum beyond that. So basically here I am assuming that n is large, it is at least r plus s, right? That is why it is starting from this. I am only having few terms here, that is why it is a lower quantity, and then I am just re-indexing it. So instead of starting from m r plus 1, I am going to start from n l equals to 0 and then re-indexing this quantity, and also okay, when l is 0, this is going to be, yeah, I am just re-indexing these quantities equals to this quantity, and then I am going to use this relation that I have already got, that is l equals to 0 to n, what I have got, p j j of r, p k k of n, and p k j, what did I do? L here, and then p k of j s. Okay. So this we have already shown that this can be lower bounded like this. Now I am going to do a little bit manipulation. I will pull out this term and this term outside. So this is minus r plus s, right? P k k of L times 1 by n times P k k. So there are how many terms here? L goes from 0 to n minus r plus n, r plus s. Okay. Okay, just we are done. Now what I am going to do, so is this clear? I have just pulled this outside and just reorganized. I have taken 1 by n and this quantity here, but now look at this. This is summation of how many terms here? L equals to 0 to n minus r plus s, right. So what I will do is simply this n I will keep in the numerator, n minus r plus s and n minus r plus s. I have just multiplied and divided by this term. Now if you look at this quantity here, this is now average of n minus r plus s terms, right. So there are how many terms? There are n minus r plus n terms, and I am also dividing by the same number of amount. Okay, now let's apply our result. What would we say as n goes to infinity? If I let n goes to infinity and this guy j is null recurrent, what did I say? Where does this quantity goes to? Yeah, limit n tends to infinity. Where does this go? So this goes to 0 as n goes to infinity, and now as n goes to infinity, you look at this, there is n minus r plus s divided by n. What does this ratio go to? That ratio goes to 1, right, because r plus n, this is a constant term that does not add much. And what does this ratio will go to? This ratio is going to be same as limit as p k k l as, sorry, n as n goes to infinity, right, because you are just skipping some finite terms here. If you look into the infinite summation of this divided by that same number here, this is going to be the limit of, so this quantity is going to be the limit of p k k of n okay. So this is going to be, let us say, goes to 1 to m, or maybe m goes to infinity, m goes to n equals to 1 to m. Okay. So this quantity is just going to this. So now what we have shown is as j goes to, sorry, as n goes to infinity, this term is going to be 0 and this term is 1 here, but this is going to be a positive quantity. This last term is also going to be a positive quantity. In that case, what we say, this limit must be 0, right, because this entire quantity is upper bounded by 0. So then what does this mean? The j is also if j is null recurrent, then k is also null recurrent. So now last thing, suppose now let us say if j is my positive recurrent, it is because it can't be transient or null recurrent. So only option you are left with is positive recurrent.